All right, good morning. So, important for you to note, you received the study guide for written test number 1. Please read it through because that will be your first written test for this course. And the programming test and written test later will be run in a very similar format, but programming test will be a little bit different. But make sure you read through the written test 1. I will give you the practice question by the end of tomorrow. For now, you definitely should really start going through the material. Absolutely critical for you to do before next Monday, which will be your written test 1. You have to make sure 2 accounts work for you 100%. Otherwise, you will be wasting time setting things up, fixing things during the test, in which case we cannot help you. Okay? So make sure your EECS account and York Passport York account, these are different accounts. I presume you got both. If you haven't got any one of these, you should really fix it. All right? So you should really make sure you can use the EECS account to log into the Williams Small Center computer. You can just drop by anytime. I believe they got much gap during the day. Drop by there and then make sure you can log in. And also once you log in, make sure you can also log into your E-class with the PPY and very often also dual mobile, right? Make sure you can do all the logging so you wouldn't waste any time during the test. All right, I cannot emphasize enough. And maybe on Wednesday, I will speak a little bit more about your written test 1, just to give you a little more idea. But for today, let's focus more on covering the materials that you're supposed to. This will be the last bit you should know for your written test number 1. And for your assignment number 1, it will be due next week. Just make sure you work on that and struggle through. If you need help, my office hour, and also the TA. I talked to you through about the email you can send to the TA. Right? We got all the help for you. You just got to do the work and get improved. All right, any question in general? All right, guys, I cannot emphasize more. We really, really cannot help you much. If you got any logging problem next Monday when you have the written test 1, you have to make sure you try it and get the issue fixed, right? You got about a week to do this. Question? Yes, it's actually likely, yeah. So, sometimes you may say, I want to do a mobile beforehand and then remember me for 30 days. In that can save you some trouble. I'm just saying, bring your mobile phone just in case you got to do it, right? Mm-hmm. Yes? Yeah, so as I mentioned on Friday, so I can finally confirm that the reservation for Williams Sports Center will be Monday. However, for any one of you who are registered for the student service, you have to come to Williams Small Center as well. Any extra time you need, I'll set it up for you. Don't worry. Just please, just come to the Williams Small Center. Just cancel with the student service. Yeah, exactly. I'll try to send an email just again to confirm. Yeah. All right, guys, read the guide and then make sure you got everything. You know everything, and then everything should be very smooth. I hope. Right, for today, I would like to continue with this example over here, which we didn't quite finish last time, but we already laid a very good foundation for that. Let me brush up with you together about what the example is about. Given this piece of Java code, we want to derive the asymptotic upper bound, of course, as accurate as possible. And in this case, we don't really have to count the precise number of primitive operations. We just need to approximate, right? Depending on how you're asked in the written test 1. I'll give you some example question when you receive it, maybe tomorrow, right? So what you're supposed to know up to this point is about how we analyze the pattern of the loop counter. If you have any doubts, you can refer to the recording from last Wednesday. I assume you know. We're saying that for I here, is going to run from 0 up to n-1. 0 up to n-1. And for every value of I, we also got a fixed number of j. It's going to be from 0 to n-1 as well. That's why you got 0 to n-1, right? That's really something you're supposed to derive. And this will be the simple case, I can tell you. We're going to do a more challenging example just in a moment. So that one will be a little more requires a little bit more formulation about the pattern, but we'll get there just to make sure. All right, so given this, how can we go from this to the final answer for the big O? All right, let's now take a look. All right, let's now continue from this. Let's now try to get an overall picture clear about how the running time is going to be derived. And then the small part for the small part, we're gonna go back to over here. All right. Let me talk about this part here. Let's separate. For this part here, we're going to calculate it separately from other parts. So this part here, we're going to talk about it. And also for this part here, we're also going to talk about it separately. Okay? If you look at line number 7, okay? Line number 7 here is part of the outer loop over here. We start with I to be 0 at the end of every outer loop iteration. We're going to increment I by 1. Right? So you can think about the body of the outer loop really has this part over here and this part over here. We're separating these two parts. All right? Let me talk about it. Think about what we're doing here is, this is one part that we have to worry about, and this is another part that we have to worry about. Okay, let's say this one here is part number 1, and this part over here is part number 2. Right, we're going to separate these two parts. Okay, let's see. Overall, it's going to be big O of, right? And for this part over here, it's going to be executed every time you have some iteration for J. Agree? When J is equal to 0, when J is equal to 1, when J is equal to 2, you're always going to execute it one time each. Also, when i's value get incremented to 1, in that case, for every value of j over here, you also have to execute this part over here once for every value. That's something to note. That's something just rely on your understanding about how to execute nested loop. Okay? So let's write down some facts for you. So P1, let's say P1 gets executed once for every value of j. This will be something very important to know, right? This part here I'm talking about. Okay? And then number 2, P2 gets executed once for every value of I. Because this part over here is actually part of the outer loop. So for every value of I, you will only execute this once. On the other hand, this part over here is part of the body for the inner loop. So to really know how many times this part over here should be executed, you should really look at the pattern over here to figure out how many I's and how many J's combination there will be. Right? That's the critical bit. Anything that's not clear here, you need this. Do you want me to say it again? Guys, should I? Okay. Look at this loop here. Do you agree? This line over here is going to be, we're going to increment the I for every iteration of the outer for loop. Right? So in order to know how many times you're going to execute this, we only have to know how many possible values of I there might be. That's all we got to do. That's the remark I'm putting over here. That's the easy one. However, for this one here, from line number 4 to line number 6, right, from here to here, this one here is part of the inner for loop. That means in order to really know how many times we're going to execute this part here, you ought to know how many combinations there are between the two loop counters, I and j. That's the idea, right? In order to know how many combinations are there for I and j, you have to do some analysis like this. All right? I hope that's clear. All right? But you got to think it through. You definitely need this. All right? Okay, let me continue. Knowing this, let's now figure out. It's going to be big O of. Let's now try with just the P1 over here. How many combinations are there for I and j? Exactly over here, right? When I is equal to 0, there are how many possibilities for j? N possibility, right? Because you go from 0 all the way to n minus 1. We got n values over there. Also, when I is equal to 1, how many possible values do we have for j? Also n. Right? We got n all the way to, for the last one, when I is equal to n minus 1, how many possible values do we have for j? Also n. Right? You will go from 0 to n minus 1. So how many possible combinations do we have between I and j? N times how many values there are for I? N times n. All right? So we got n squared combinations of I and j. This is a very critical insight you ought to know in order to really derive what's happening over here. All right, so let's now do the big O, and then I can take your question. Okay, let me just wipe this out. You don't need it. It's going to be the big O of, let me move this to here. For P1, it's going to be n squared multiplied by, and we know that every time we execute this, it's going to be 1. No loop in this body, right? Just 1. And plus, what about this part over here? I plus plus is going to be executed n times because we got n possible values for I, right? I from 0 all the way to n minus 1. N multiplied by 1. Plus, finally, outside the entire nested loop, we also got return. All right? Plus 1. Right, let's make a note. 1 here is about line 4 to line 6. Line 4 to line 6. The 1 here is the I plus plus, which is line number 7. Okay? The 1 here is the return, which is line 8. And then n squared over here is exactly the number of combinations of I and j. And the n here is the number of iterations of outer loop. Outer loop, right? Once you get this, you're getting very, very close. How do we add it up? Let's just do one more step. N squared plus n plus 1. And we only keep the highest term and drop its multiplicative constant. So we got a big O of n squared. That is the final answer. Of course, if the question doesn't really ask you to provide any steps, you can sketch. But if it does ask you to show the work, you have to be very rigorous about the process of deriving it, which is what I'm trying to explain to you. All right, time to take question. Yes?
This kind of a reminder piece. So when we have line 4 to line 6, we have it as 1. We're not referring to the primitive operations, are we?
Okay, so here, okay, let's answer that part first. This part over here, we are trying to approximate how many primitive operations they are. I simply put 1 because they are all primitive. It doesn't really matter if you say 1 or 4 or 5. That one will be dropped for the lower term anyway. So that's why I only put 1.
So because we're not focusing on the actual primitive operations?
Yes, we're approximating. That's important, yeah. However, if I change the question here to say you want to calculate precisely how many primitive operations there are, then you got to be very precise. It's different. Yes, go ahead. Okay, very good question. The question was, is it correct every time if you have this pattern over here, let's say I from 0 to some upper bound, j from some value to some upper bound, if the upper bound is simply just n over here, yes, you can say n squared. However, you might see some trickier loop, which we're going to see. In this particular pattern, yes, you can know that's n squared. However, if I do ask you to show the steps, you have to show something like this to tell me how you figure out there are n square combinations of I and j. That's important.
So that same process of the number of times that the loop runs by itself, if there were no outer loop, the number of times the outer loop runs, right?
Yes, exactly, yes. I think once you derive a pattern like this, it will be very easy for you to count. Yes, question?
You have an example of a nested for loop that would translate to something else other than ON squared?
Sorry, say it again. I don't quite catch you.
Do you have an example of a nested for loop that would translate to something else other than n squared?
Okay. For example, the example I gave to you last time, like here, right? Okay, very quickly, okay? Let's say now the upper bound for the I is now changed to some constant value. Even though 10,000 over here is pretty large, but it is still. Think about what's happening here. 10,000 might seem very large, I agree, practically. But we're talking about theoretically, right? 10,000 over here is really is really n to the power of 0 multiply 10,000, right? So this part here, you can definitely drop it anyway. So you only got 1 left. That's still constant, right? So here, this is only constant, but this will be according to the length or size of the input. So overall, you got n multiplied by 1. In that case, you got n. So having a nested loop doesn't really mean you get n squared always. Similarly, if I got some very large constant over here, 1 million, 1 billion, still, theoretically, it will still be just constant, right? Right, guys, nothing new. This is something I asked you guys to think about last time, right? So just don't forget, right? So here, because thanks to your classmate, I try to explain it a little bit further, right? Okay. Any question about this? I would say this analysis over here, of course, is slightly more challenging than just like a find max. It's because you got nested loop. Is this the most difficult one you can get into? Not really. We're going to see something more challenging. But if you really grasp the principle over here, the more challenging one should be rather straightforward. You just need to be more careful about deriving the pattern here. That's it. All right? I'll take more questions, and then yes. Yes.
That I plus is supposed to be like for the for loop on line 3, right?
Yes, that's correct. So, yeah. Okay, I see what you mean. Okay. Guys, take a look at this line. That's what your classmates are asking. Look at line number 7. First of all, this guy here belongs to the outer loop. And because it's put at the end, so that means at the end of every iteration for for loop, when I is equal to 0, when I is equal to 1, all the way to n minus 1, you're going to execute it once. So that's why only n times. Now your question might be, what if I move this guy here to the header of the for loop? The answer will still be the same. Because the meaning of the for loop, like this way, is going to execute whatever that's in the progress at the end of the loop. It will be as if we wrote it here. You will still have the n over here, yes. But if I put I++, for example, to right over here. Tell me the line number. You mean here? You mean here, right? Here or here? Yes. This guy here? Yes. It will still be the same. It will still be the same. Just remember, this progress over here either has to be executed here, or it has to be executed here. But in runtime, it's going to be at the end of the loop anyway. Yeah. Maybe the order of the terms is slightly different, but the final answer should be the same. Because putting either here or here, it wouldn't change how it would behave, right? Any questions? Any more? Okay, got to be maybe last one again. Because this one here, you start with I being equal to 0, right? And the last valid value that's going to make this expression true will be n minus 1. So you go from 0 all the way to n minus 1 inclusive. And we talk about some nice little formula I thought you guys would know from the previous math course. If you don't know, now will be the time to learn it. If you got an interval of integers from a to b, all right, inclusive. Let's say go from 2 to 3, 4 to 10, 4 to 100, and etc. Okay? In this case, how many numbers will there be in that range? It will be the upper bound minus lower bound plus 1. All right? You can easily justify that, right? It's not something that's really new. Good. Are we good? Okay. I'll take silence as you're fine, right? Guys, otherwise you should just interrupt me. I'm serious. I don't mind covering less for your written test 1. Whatever I cover today, it will be on your written test. So I want to make sure you really got it. All right? Okay, you can come back to me later. Okay, next one here. We got 2 more examples. For this one here, let's take a look. This one here will be rather straightforward. Why don't you guys take a look just for 1 minute and tell me what you think the most accurate asymptotic upper bound is. Here we have 2 loops. Do you think it's immediately n squared? Okay, if you don't think that's the case, that's a good sign. You don't want to make a prejudice so quickly. Now what should that be? Let's say for this one here. Not yet. Let's think first, right? I'm going to give you a classmate sometime. Take a moment. That might be just what you'll be given next week this time. All right? Any guess? Ferrets. You think there should be n squared? Oh, okay. But don't we have 3 loops over here? 1 loop here and 2 loops here. 3 loops. Shouldn't that be n cubed? Okay. They're kind of independent, exactly. So the main lesson from this example over here is when the loops are not really nested with each other, you shouldn't try to multiply, right? You try to add, right? It's a simple rule you want to keep in mind. Okay, let's take a look quickly. Line number 2, this one here should just be constant just by itself, not in any loop. What about this one here? This one, like a find max, right? You pretty much know how to do things like this. This will be just n by itself. And then this one here, line number 6, that one by itself is also constant. And then this guy over here is exactly like what we just did. This guy here is like what we did previously over here. Pretty much the same. You can see here you got 2 loop counters, j and k. Each one of them is bounded by n, so you got n squared. Finally, if you look at the return, that one there is also 1. So how do we add it up? We go off 1 plus n plus 1 plus n squared plus 1. And what's the highest term? N squared, right? They go off n squared. That's the final answer.
So that's like the worst case.
Sorry, say that again?
So the n squared is like the worst case runtime, right?
No, yeah, worst case. Yes, exactly, worst case. We're all talking about worst case. We never talk about best case. Best case might just be constant. Like you never get into the loop, right? We don't talk about best case, worst case only. All right? Is this okay for you? Final one. That's a challenging one. All right? I want you to take a look first. First of all, the final answer I can tell you is still n squared. But the way you derive it requires more, you should be more cautious about how you derive the final answer. That's something I care. All right? If I only ask you about what's the final answer, you can tell me n squared. That's okay. But I need to know in the exam, or if I require some written answer, how exactly you derive the n squared. That's something I'm going to do with you here. What you need to know, the critical thing. Once we solve the critical thing, everything else will be the same as what we did earlier over here. Okay? What you ought to know is, how do we figure out a combination of I and j? Is there a pattern? That's a critical question to ask. Look at header over here. And then, what's really the pattern of combining I and j, like a pair? That's the question you want to ask yourself. All right? Let's take a look. It's not too difficult, but once you get a pattern, you ought to know how to add up things together. That's something we need to review too. All right, let's do one thing at a time. I starting from 0 all the way to n minus 1, right? You can see that's strictly smaller than. Okay, and we do progress. And back to your question before, if I put I++ over here, it wouldn't change our rule, the same, okay? So let's now talk about a pattern of I and J. Okay, I is going to be 0, 1, I'll do 2, all the way to I is equal to n minus 1. I'm pretty sure you're fine with this, right? So far, so good. What about the next one? J starting from not 0, but I, all the way to n minus 1. Okay? When I is equal to 0, what will be the value for J? From what to what? 0 to n minus 1, right? Okay. What about when J is equal to 1? Oh, sorry, let me say it again. What if when I is equal to 1? What will be the value for J? Starting from, yes? Absolutely, thank you. Absolutely. If you're following so far, it's a very, very good sign. Let's do one more. J will be 2 all the way to n minus 1. Okay, final one. When I is equal to n minus 1, J will be from n minus 1 to n minus 1, just one value. All right? If you look at the value here, it's more like a triangle. That's why I say triangle sum, just for your information. All right? Now we need to know how many combinations there are. Right? You can see here we got 0, 0, 0, 1, 0, 2, all the way to 0, 2, n minus 1, when I is equal to 0. How many? How many combinations do we have between I and J when I is equal to 0? How many do we have? N or n minus 1? N, okay. So this one here, just for your information again, we're calculating the size of the interval from 0 to n minus 1, right? By definition, it's going to be, the size will be n minus 1 minus 0 and then plus 1, which will be n. You do the same calculation as before. All right, what about when I is equal to 1? How many possible values do we have for J in this case? Is it still n? No, n minus 1, right? Because in this case, we are counting from 1 all the way to n minus 1. If you look at the interval here, if you got 1 to n minus 1, using the formula, n minus 1 plus 1. This one minus this, and always plus 1. That will just give you n minus 1. All right, let's continue. When I is equal to 2, what would that be? N minus 2. All right, I'll leave that to you. The size of 2 to n minus 1 is n minus 2. All right? You can figure that out easily by using the formula. All the way to, what about the last one here? When I is equal to n minus 1, there's only one possible value for J. So how many combinations? 1. Now, we have to add up these all together. Before that, let me just sketch how the big O is going to go. It's going to be something like this. You're going to say the big O of 1. This will be line number 2, right? Just declare the variable. Plus, this one here, we only got this as the body of the inner loop. So that's the only thing we got to consider. Before, we also had to consider like I++ here explicitly, but here we don't need to. Of course, if you want to, that's also going to be executed at the end of the loop if you want to, but it's not required. Okay? Oh, sorry, too far. So how about this one here? It's going to be some number over here multiplied by what will be the running time for this? Approximately, just 1. Just line number 5 alone, right? Multiplied by 1 over here. So this guy here, oh, this one here is still blank. I'm going to fill it in a moment. So this will be line number 5. Plus, outside the loop, we got line number 6, right? That one is also 1. Line number 6, okay? So what's really uncertain is about this. This one here is about number of combinations of I and J. That's something we ought to figure out. Okay? N combinations when I is equal to 0. N minus 1 combination when I is equal to 1. N minus 2 combination when I is equal to 2. All the way to just one combination. How do we add up all these terms together? Do you guys know what a arithmetic sequence is from your possibly high school math or maybe from calculus course, right? Yeah, you want to say something? Go ahead, please.
So that's basically equivalent to the sum of all the numbers from 1 up until n, which is a famous formula.
Exactly. So let's review that formula then. Exactly. So what we want to calculate is the sum of an arithmetic sequence. Okay, let's do that quickly. What we are talking about here is like this. The sum of arithmetic sequence. It has this general form. Let's say over here, you have I plus C. I'll give you one example. I just want to give you the formula first. Plus I plus 2 times C plus all the way to I plus n minus 1 times C. Yeah. So this is called the first term. Okay, so this is, C here is the constant. Let me see. Some constant over here. Think about to go from here to here, you actually do plus C. To go from here to here, you also plus C. From here to here, all plus C, all the way. That's an arithmetic sequence. What will be one example? If you try what we did here, example, 1 plus 2 plus 3 plus all the way to n, right? You can see here, this will be the first term. Right? What's the common addition? Plus 1, right? Plus 1, and etc. All right? And the formula tells you the whole thing is going to be the first term plus the last term. Multiplied by C. And then the whole thing multiplied by the number of terms. How many terms are there in this n? Okay? One way to see that, you can think about this part over here is like an I plus 0 times C. So you got 0 here, you got 1 here, you got 2 here, 0 all the way to n minus 1, so n terms. Okay? And then divided by 2. That's the formula. First term plus the last term multiplied by the number of terms divided by 2. Okay? How do we apply that to here? First term will be 1. Last term, n. Number of terms from 1 to n, how many terms do we have? n, right? Divided by 2. You don't necessarily have to be bothered too much by this general form, but that's only for reference. All you need to know, if you want to know the minimum, you need to know how to calculate the sum of this sequence over here. It has some first term, it has a last term. Add it up, multiply by the number of terms, divided by 2. All right? That's all you need to know. Number of terms. Right? And for this one here, it's going to be just this one here. What would that be? It would be n squared plus n divided by 2. All right? What's the asymptotic bound for this one here? N squared, because that's the highest power. You can try to rewrite it a bit. N squared divided by, how about this? Think about it like this. 1 over 2 times n squared plus n divided by 2. Drop the multiplicative constant, drop the lower term. You only got n squared left. This one here is big O of n squared. Right? It's a very important formula for you to recall. Let me finish that, and then I'll take a question. Okay? So with this, we can fill it in. What's really unknown is this one over here. This one, as we just calculated, this will be just n squared based on the sum of the arithmetic sequence. Why do we do that? Because based on the observation, that's the sum we need to add up for the loop pattern. If you're required to justify the steps, you ought to show this particular sequence over here. Okay? Okay, let's finish that, and I'll take your question. This one will be basically, okay, so how do we add up? So 1 plus n squared plus 1. That will just be big O of n squared plus 2. And drop this lower term. You get big O of n squared. That's the final answer. Even though the loop pattern is actually trickier to observe, asymptotically, it's still n squared. Okay, so it depends on how the question asks you. If the question only asks you to give one answer, you can say n squared. That's fine. But if the question asks you to justify, that's something we would like to see. Okay. Question? Yes, go ahead.
If you break the series down into pairs where you're summing the first element and the last
Yes.
one and the second and the second
Yes.
one,
Yeah.
all add up as one, and then
Yeah. Absolutely. I think that was a famous story by the genius Gauss, right? Just yeah, I wouldn't mind mentioning that quickly. One example would be, how do you understand this formula here, right? Think about if you're trying to add from 1 to 10. If you look at beginning term and the final term, this is 11. If you look at here and here, it's also 11. 3 plus 8, also 11. It's going to be the same, right? So that means they will be n over 2, because every time you talk about a pair, you divide it by 2, basically, okay? Multiply by n divided by 2, right? And in this case, n would just be 10, because you have basically 5 pairs of such sum, right? Okay, that will be your answer. That's another way to see the formula. But if you just want to memorize it, that's also fine. We wouldn't ask you to justify this formula. You just need to know. All right? All right, any question about what we talked about so far? We okay? All right, if you guys are fine, then I would say that's it for asymptotic analysis. We're done with that particular lecture. Okay? So that's the example we talk about today. And then, right, so this part here just repetition. So in order to really do Java, assignment, you ought to know how to use debugger, how to derive methods from JUnit tests, right? That's something I assume you will catch up if you need it, because that's something you're supposed to be done in 2030. All right, that's about it for this lecture. Any question? We're good? Okay. Why don't we take attendance and take a short break, and then I'm going to cover some slides and material from the next lecture. Whatever I'm going to cover by the end of today, that will be covered in your written test 1. All right? Why don't we take attendance quickly? All right, just get yourself ready. Poll. Doesn't matter. All right, you can now check in. Okay, please do it now. If you got any problem, please come forward right away. All right? Any issue? Everybody's okay? Yeah, if you got issue, come forward, please, right away. Don't wait, just come. All right? I'm just about to stop it. Once I stop it, yeah, I'll give me a moment. Let me just wait a minute. Yeah, give me.
It says check and fail.
Don't worry. Oh, we'll let you sign up. Don't worry. Yeah. All right. Let me close it. Thank you. And let's take a 2 minutes break. Don't go too far. Yeah, come on. Did I allow you to check in? Okay, no worries. Yeah. Yeah, just find your name here and sign. I have a pen. Don't worry. Yeah. All right, got any trouble? Please come right away, right? Yeah, you can just sign here. I guess sometimes works for you, sometimes doesn't.
Yeah,
Funny.
Before it was just a laptop thing, but then on my phone right now it just says I'm somewhere else on campus.
Are you using Wi-Fi or the data?
Wi-Fi here.
Wi-Fi here. Next time, maybe try the data. That might work sometimes. Yeah.
Does it ask, do I need to put my signature in?
Please do. Please do. Put your signature here. Okay, awesome. Okay, I'll let you do it. Yeah, guys, any trouble, please come forward, and then we'll do the sign up here. Okay? Today we seem to get more of you having trouble, but yeah.
Professor,
Yeah.
for the assignment, is it okay if I make use of the Streams API for like some of my solutions?
If you, sorry, say it again. If you,
If I use the Streams API, Java Streams?
yes, that'll be fine for assignment, no problem. Yes.
I have some question about the assignment one.
Mhm.
And I see the assignment one instruction set, it is allowed to create some new attribute and a helper method. And you gotta make some declaration, right? I make a comment saying that this method is a helper method of text 4. Is it okay?
That's
or-
fine, yeah. You can declare any helper method as you see fit. Yes.
So any other declaration should I add into it?
Yeah, if you feel that it's necessary for your implementation, yes, you just add them. Whether you put comments or not, I would say I'll leave that to you. I think for this course, we focus more on the coding itself, right? So I think it would be very good practice to put the comments for your code. Yes, I would encourage you to do so. Yes. All right. Hi. Yes, of course.
China A1, are you supposed to upload it to like GitHub?
GitHub for assignment number 1? No, you don't need to.
Okay.
You don't need to. I would say GitHub, like a private repository, is only optional, but it's a very good practice for you to maintain. So I would encourage you to do so. If you got any trouble, let me know.
Okay.
Yeah. So after the semester is finished, you can feel free to make it public. But within the course, please make it private. Let me know if you got any trouble, right? Okay. You signed already, right?
Yeah, I did.
Okay, good.
Thank you.
It recorded my answer, but I don't think it recorded the attendance because when I go like this, it doesn't say for today.
Okay. So, okay, let me why don't you sign here, just in case. Yeah.
Maybe it's because you haven't closed the poll yet?
I already closed, I believe. Yeah.
Or the class session.
Yeah. All right, guys, we're starting 1 minute. Just get yourself fresh, and then we talk for a little bit more new materials today.
I just want to make sure I'm understanding correctly. So we have, because in each ICE we're going from 0 through to n. Correct?
Yes, yes.
But because in the J section we're going from, we're decreasing as we go along to the number of
Yeah,
iterations.
you want to focus more about how many combinations there are. That's the key term. Think it through. Maybe after today, and then come to me if you got trouble.
Okay.
Yeah. All right, guys. Why don't we get started again? All right. We're gonna about 35 minutes-ish, and then we'll see how much we can cover. All right. Okay, so it will be a new lecture series. Okay. So this lecture here is more about talking about two foundational blocks for algorithm. arrays and also linked lists. Arrays are something you have been studying, in your first and second year, 2030, a lot, but I think I might just be able to give you some insight today, maybe a little bit, now that we learned about asymptotic analysis. And today we wouldn't really touch linked lists. My hope is we can start talking about linked lists from Wednesday. But don't worry, we're not going to cover that in your written test 1. We'll only cover up to what I covered today, right? Okay. Let's now do it, okay? And as usual, interrupt me, okay? Right, we're going to talk about basic data structure, arrays, and linked lists. And for linked lists, singly linked versus doubly linked. That's something we'll get into, okay? For now, you don't need to worry. But we're going to focus on arrays today. And there will be 2 sorting algorithms. There we go. Remember, I listed maybe about 5 or 6 the other day. There we go. We got 2 today. So what about these 2 algorithms, selection sort and insertion sort? I think this will be the best plan for us. In the class, I'm going to give you the most intuitive thinking about how these 2 algorithms work so that you can translate the thinking into any coding, Python, Java, C#, whatever, once you get the idea. And then I'm going to take some working Java implementation and do the exercise of deriving its asymptotic upper bound with you, like what we did before the break. These are the 2 things I hope to complete today. And then there will be some assigned tasks to you, which is about tracing the Java code of these 2 sorting algorithms. If you are confident enough to trace just by yourself, that's okay, you can do it. Otherwise, I do have some very good video to walk you through the process. I'll leave the choice to you. So these are the things I want to do. And hopefully we can finish that for your written test 1. If we cannot, we'll see. We'll see. That's the plan. And then later on, we're going to talk about linked lists. But that will only be from Wednesday. All right, for arrays. Very quick slide just to summarize what you know already. Summarize. Array will just be a sequence of index elements from 0 to a.length minus 1. And array has a fixed size always. However, a little bit heads up. Later on, either I will give you guys some optional study or we'll talk about it in class. We'll see how the time can be managed. There are 2 resizing strategies. Fixed increments versus doubling. And to really do that analysis to see which one is better asymptotically, we ought to do average case analysis, which is something that's more challenging. But we'll see when we can cover that. Don't worry, just heads up to know there's such thing. And what are the operations you can do on an array? Primitive array. I'm not talking about Java API arrays class. That's not what I'm talking about. I'm talking about primitive array in Java. You can do accessing, right? We talk about it's a primitive operation. So constant time, straightforward. What about updating? If I want to update certain index by using assignment, you can, how many primitive operations in that case? In this line, I plus 1 will be 1. Indexing into a of I plus 1. Oh, let me be precise. If I got AI assigned to I plus 1, for example, okay? How many primitive operations? Right? Any number? Is it just 1? I'm talking about precise number, not approximating. 4, sounds promising. Here is 1. Indexing is 1. Assignment is 1. Indexing is another 1. All right? 4. Mm-hmm.
I was just going to say, even though there are like 4 pairs, it's still going to be constant.
Yeah, of course. 4 itself is n to the power 0 multiplied by 4. If you drop it, it will still be constant for sure. Absolutely. All right? All right, let's go back. And that'll be constant. And what about inserting, removing? So this is something you want to keep in mind. Whenever you want to use array to implement algorithm, this is what you should know. If the algorithm depends much on indexing and also assigning somewhere to the array, then the algorithm most likely will be efficient. However, if your algorithm has to somehow insert and remove somewhere into the array, it's destined to be something not efficient. In that way, you may have to choose another alternative, which is linked list. But linked list will be the opposite, right? That's something we'll talk about. I just want to give you a feel. For now, you ought to know the efficient operation for an array will be accessing and updating. But if you want to insert and remove, it's going to be very inefficient. It's going to be beyond constant time. I'll give you one example. Let's say inserting, okay? Let's look at this together. By the way, if you only look at this fragment of code, all right, that's something we'll do as well at the end. Without understanding exactly the logic for this fragment of code, you can already do approximating the running time. You can already do it. Right? Let's do it a little bit later. Okay? But what I want to do now is to give you some idea about how this one works. It's a very typical way to really say, I got an array, let's say of 10 elements, and I want to insert maybe to index 5 into the array. But what about the original index 5, index 6, index 7, all the way to the end? I need to shift them somehow. But the shifting operation is going to be expensive. That's something we're going to talk about now. Okay, let's see some example. For now, you don't need to worry about this one just yet. Not yet. Okay, let's look at some example. Insert at is going to take some string array, the size of the array, some element, new element I want to insert. This is where to insert into. So I here is where to insert. Where to insert. Okay. Let's take a look at one example here. So this will be one example call to the method. Insert at, I'm passing an array with Alan, Mark, and Tom. So this is the input. So input will be Alan, Mark, and also Tom. All right, these are the 3 elements. And the 3 here is simply just a.length. That one there is fixed. Just easier for us to do the analysis. Now I want to insert Jim into index 0. What does that mean? That means after the assertion, it's going to return back to me another array. Number 1, because it's going to insert some new elements. So the size of the array is going to increase. Rather than 3, it's now going to be 4. Number 1. Number 2, I want to insert Jim into this particular index 0. Let's put Jim first. And then what happened to Alan, Mark, and Tom? We don't really just overwrite their value. That's not what insert really means. What we need to do instead will be Alan that used to be at index 0 now should be shifted to index 1. Mark that used to be at index 1 should now be shifted to index 2. Tom used to be 2, index should now be shifted to index 3, and etc. We've got to do some shift operation. As you can see, I'm only showing you one case. In general, the shifting operation ought to be done by some loop. Whenever you have some loop, that might get that to be linear, right? That's something you want to have in your mind. Let me finish this example here, and then we'll do one more. So basically, you're going to say from 0, shift it to just 1. So this will be Alan. From 1 here, shift it to 2. So that'll be Mark. From 2 here, shift it to 3. That'll be Tom. The shifting operation is going to be the expensive one. But we'll see. All right? Are we okay so far? All right. Let's now see exactly how we can implement this. I'll do one more example, and then we're going to figure out the running time by approximating it. Okay. Let's say we consider this guy here, insert at. Still Alan, Mark, and Tom, let's say. Alan, Mark, and Tom. That's the input. 3 here, fixed because the input size is 3. We want to now insert Jim at index 1. All right? So Jim should be here, basically. Let's do the rehearsal. If Jim need to be here, something should come before Jim, something should come after Jim. Both, in general, are going to require some copy operation using a loop. So that's why you see one loop here and one loop here. That's why. All right, let's see how to do that. Okay? Let's now try to trace the code very quickly, line by line, by executing this scenario. And then we'll talk about how to approximate it. Okay? In order to do this, let's say line number 1. We're going to create a new result array, and the size is going to be n plus 1. For example, if n is equal to 3, if n is equal to 3, that means the new array is going to be 4. Right? It used to be 3, but now we need 1, 2, 3, 4 for the new insertion. Right? So result over here, we just got this, a new array. Okay? And let's use the first loop. The first loop over here is actually going to do the following. Starting from j equals 0, go all the way to I minus 1. In our case, what's I? This is I. All right? So that means we're going to go from 0 all the way to 1 minus 1. 0 to 0, only one element. What does that mean? For this loop, we're going to copy everything that should really come before Jin into the new array. Okay? Jin is supposed to come to index 1. So now we got to make sure index 0 should really be the original index 0 element. We should copy that over. Right? That's what this loop will do. Okay? Let me make some notes for you. You got to think through this, this one here. Let me give you some intuitive explanation here. Copy input 0 input. How about this? Starting from input 0 all the way to input I minus 1 to the result. Right? When I say input over here, I really meant the A over here. All right? That's the first loop. What would that do? Because 1 here will be the upper bound. So only going to copy all the way to index 1, just Allen. All right? So Allen is now going to be copied to here. That's the only thing we do for the loop. Are we okay with what we have done so far? You can see here, result j will be aj. Result 0 will be a0. Think about result. Index 0 will be a, the input 0. That's basically what we do for the very first iteration. Okay? Let me make it green. Let me just do it again. So we got result 0 will be a0. And then we go to the next line, which will be just to assign result at index I to be the new element E. In this case, we're going to assign result at index 1 to be the new elements Jin, because it's supposed to be inserted at index 1. Right? That one there, we're going to put Jin over here. And what's remaining? The remaining one will be, we ought to really do copy down this subarray over here conceptually into this subarray over here. To do it, you got to do a loop. What's going to happen? That part over there is going to be, let me use blue here. So we already got result of 1 is Jin. That's something we just executed. After that, we're going to say result 2 will be A1. Also, result 3 will be A2. What does that mean? Result 2 is going to be assigned to A1. Result 3 will be A2. You can see there's only some index from j to j minus 1. That's exactly the pattern. All right? Let me finish this, and I'll take a question. Give me one moment. Let me finish this. So this one here is going to copy. Copy A, I minus 1 to the result AI. I'm just trying to be consistent with what's being written over here, right? And what's going to do is the first one is going to copy Mark to here. Second iteration is going to copy Tom from here to here, right? So you want to watch out for the indices. For example, from 2 to 3, so this is exactly what you had. Result J is assigned to A, J minus 1, right? Focus on the index over here. That's how you do the tracing. Up to now, I'm really trying to show to you how the algorithm works. And it seems like it's working. And the next step is to derive the asymptotic upper bound. That's most accurate. And we're going to do that. I'll take a question first. Very good. Thank you. All right, let's now do the asymptotic upper bound. I can tell you that this one is not too bad. In order to derive it, you don't necessarily have to know exactly how it works. It's a different problem, right? What we did was to trace. But now to really derive the asymptotic upper bound, let's do this. Let me talk about this line here. For this line here, what's that going to be? Well, arithmetic, and you can think about object creation, it's just a constant. That's something I didn't really mention, but you can think about object creation is a primitive. Object creation is a constant time operation. You can assume that, always. So we got one here, assignments, and that's it, right? It's still constant. This one here is definitely constant. And this one over here, the body, indexing, assignments. This one here is also 1. However, how many iterations do we have over here? How many iterations? From 0 all the way to I minus 1. I iterations, agree? I iterations, okay? I iterations. So this will be big O of I iterations multiplied by 1. Guys, why I? Because J will be from 0 all the way to I minus 1, right? Let me just write it down explicitly. J would just be from 0 all the way to I minus 1. So how many numbers are in the interval from 0 to I minus 1? I. Let me talk about it a little bit more, and then. And here, what will be the big O of this? OI, I agree, but I here is not very useful. We want to think about what's the worst case for I. I is what you can pass as input over here, right? The larger the I is, the larger this term would be. What will be the largest one for I? N, exactly. If that's what you're thinking about, you're right. Okay, good. And this one here will just be big O of N. I here, worst case, when I is equal to N. All right, so far so good. And then let's move on. What about this one here? Just indexing and assignment, so that's also 1. Let me highlight what we have got so far. We got this one here. We got this one over here. We also got this one over here. Okay? What about this one here? How many iterations do we have? From I plus 1 all the way to N. From I plus 1 to N. If you use the little formula we talked about, I'll make it larger for you. N minus I plus 1 and then plus 1, which will be N minus I, right? N minus I iteration. And for each iteration, indexing, assignments, and arithmetic, also 1. So think about this guy over here is just 1. But it's going to be big O of N minus I multiplied by 1. All right. Now, how do we figure out this number here? What's the worst case for this? The worst, because it's minus over here, right? In order for this term to be the largest, I ought to be the smallest. The smallest you try to subtract, the larger the subtraction should be. Agree? Now, what will be the minimum case for I? Given that I is a number here for index. 0, which is exactly what we did over here. It's the worst case, in this case, for the second loop, not for the first loop. Right? But we can talk about it independently. So here, the entire n minus I, the worst case is when I is equal to 0. Right? So it will still be big O of n. All right? So, final one. What about this line here? Just return. Just 1. All right? Now, how many have we got? We got 1, we got n, we got 1, we got n, and also we got 1. Overall, it's going to be big O of 1 plus n plus 1 plus n plus 1, which will be big O of 2n plus 3, which will be big O of n, right? Obviously. So inserting into an array is a linear time operation. Later on, we're going to see if you try to do something similar to a linked list, it could be just constant for some reason. But we're going to talk about it later. Yes, question? Yes, exactly. Yeah, I'm trying to, I didn't really, I'm trying to approximate. So that's why I didn't really talk about even this. This will be 1, of course, this will be 1 as well. I'm just trying to simplify the things a little bit for our discussion. You think about this will be some constant, you may need to add that, but they will be dropped anyway. Right, for sure. Say it again? Yes, exactly. So think about, we talk about the worst case, right? We don't need to think too much about the logic. We talk about this loop here, it's not nested. These two loops are not nested, so we talk about it independently. The worst case for this loop will be when I is equal to n. That's big O of n. The worst case for this one here will be when I is equal to 0. That's also big O of n. We just add them up together. Mm-hmm. All right? All right, any question about this? All right, everybody's okay? All right. The next part will be about some case study. We want to study insertion sort and selection sort. This is what we're going to do. The sorting problem. Sorting problem is a very classic one in computer science and software engineering. So you got an array of n numbers. Let's say this is one example, 3, 4, 1, 3, 2. You want to have an output. Usually you would say it's a permutation, reordering of the input in a non-descending order. I want to clarify some terminology very quickly. There are 4 different things you might hear in the literature. Descending, ascending, non-ascending, non-descending. You ought to know what they really mean. All right? Let's take a look first. And then we'll talk about, so these are the 4 possibilities I just enumerated. Okay, let's now talk about the terminology quickly. Okay. Okay, so let me just make sure. Okay, good. Let's talk about maybe decreasing or descending first. This one here. Decreasing or descending. I'll give you one example here. Let's say 5, 4, 3, 2, 1. That one's obviously decreasing, strictly decreasing. If you're trying to find some maybe AI over here, another maybe AJ over here, it's always guaranteed. AJ is strictly smaller than AI. Guarantee. And there's also some implication here. If you say an array is sorted in decreasing order, that means there's no duplicates. Because, for example, if I got 4 and 4, in that way, 4 is not strictly less than 4. So you wouldn't satisfy the property. So when you say it's decreasing, there's no duplicate. Okay, like that. Let's also do increasing as well. Increasing would be, let's say, 1, 2, 3, 4, 5. Okay, it's going to go this one instead, right? Okay. And that one there, if you got AI over here, for example, if you got AJ over here, right, the later elements, it's guaranteed AI is strictly smaller than AJ. Notice that I swap already, JI and IJ. Just notice that, okay? And also, increasing also doesn't allow any duplicates, no duplicates. So far, so good. And let's now talk about non-decreasing or non-ascending, something like that. Let's start with the first one. When I say non-descending, it's by definition, for any I and J indices, oh, sorry, let me, that's okay, actually. I'll show it to you. Let's say it's not the case, it is descending. That's the none really mean, right? Logical negation. I'm sure you guys have seen that already, right? It's not the case that it's descending, okay? And we know that descending over here, by definition, which we just did, descending over here means we got AI larger than AJ, right? If you got I and J over here, it should be descending like that, all right? If you got AI here, and also AJ over here, right? AI should be larger than AJ. And now, if we apply the negation over there, it would be equivalent to AI less than or equal to AJ. So that's really something I want to show to you. If you want to talk about non-descending, this is the relationship. Okay? One moment. So what you're saying is, it could be something like this. As long as it's not descending, it will be okay. Right? It is not the case, it is descending. It could be increasing, or it can be just staying flat. Either way. Okay? Think about this one here. You think about these two. If this is AI, this is AJ. This one over here is about AI is strictly smaller than AJ. But if you talk about this part over here, that's also legitimate. This one over here is about AI is exactly equal to AJ. That's why you see I got less than or equal to. Right? So if you look at how the things are going, non-descending means you cannot just go increasing. Sorry, you cannot just go decreasing. This is not allowed. As long as you don't really go this way, it can either be increasing or it can be staying flat. So one example would be, let's put 1, 2, 2, 3, 4. You can think about the 2, 2 over here is like the 2, 2 over here. And the 1, 2 over here is like the 1, 2 over here. Right? We need to clarify this. Yes? Because we're comparing, like an individual element in the array. So nothing about linear or something. I'm just trying to show you the trend of the elements. Yeah. So you want to know whether it's increasing or decreasing. That's the plan. That's the point. Yeah. Yes.
So would a increasing line also count as non-decreasing?
Increasing line?
Yeah. So like.
Oh, you mean just like that, right? Yeah, that's fine too. Yes. I'm just saying that you can either go for this or go for this. Yes, very good. So here, duplicates allowed. All right, like that. And what about non-ascending? As long as it is not decreasing. Sorry, non-ascending means as long as it is not increasing, you'll be fine. Right? So how do we draw that quickly? So it could be decreasing here, or it could be staying flat, or it could be also decreasing. Okay? And one example, 43321. For example, you can see the 3 over here is like this part over here. Also 2 over here is like this part over here is dropping. And if you also got this one here, that's also considered as legitimate. That's also fine because it's not ascending. Also for this one here, you can also go something like this, increasing. That's also fine. Right, so these are the 4 terms you ought to know very well about what they really mean. Okay. Okay. Are we good? Yes. Yes, that's correct. For this one here, if you got either decreasing or increasing, there's no duplicates for sure. Yeah. For these two, you do allow. May or may not be. Okay, good. All right, we got about 4 minutes left. Okay. So I would suggest, okay, I think to be fair, I don't want to rush too much. Why don't we say your written test number 1 is only going to cover up to slide number 4. Okay, we wouldn't be able to maybe cover about how insertion sort, selection sort work, but that's okay. We can definitely do it on Wednesday. Whatever we'll start covering on Wednesday, you don't need to worry about it for written test 1. But I think it might help. It might help, but it's not required. Okay. All right, guys. I think I'll let you guys go earlier today. Okay, we got about just a few minutes. So your written test number 1 is going to cover up to slide number 4 on this new lecture, especially the example we just talked about. If you got any trouble, let me know during the office hour. Okay, I'll see you on Wednesday.